Hello everyone, Human Hard Drive here. Today I'm going to be talking about what an RTOS is. Now, I'm doing a series of videos with the STM32F4 Discovery Board, and I'm going a different direction with that. Instead of doing hardware stuff like with what we do with the AVR and the ATmega 328P, what I want to do is take a little higher level look at the architecture, specifically dealing with an RTOS, a real-time operating system. So, what is an RTOS? That's what I'm going to answer in this video, and hopefully that will clear up some things when we actually delve into the board and all of the things you can do with an RTOS. Specifically, we're going to be using the Chibi OS. So if you want to have a look at that before we start the videos, by all means, go ahead and start going through the documentation. This is going to be a little more formal. Going to be throwing out some big words, some concepts. I hope you can all follow. I hope I make this simple, and if you have any questions, remember, I'm happy to answer them. So, what is an RTOS? The first thing an RTOS does is something called abstraction. What does that mean? Well, it introduces the concept of drivers and layers. Now, with the AVR and the ATmega 328, what we do with AVR-C is that a lot of times you have to, well, not a lot of times, you always have to muck around in the very inner workings of the chip. You've got to deal with registers, you've got to deal with bit shifting, you've got to deal with timing calculations, you've got to deal with interfaces, communication protocols. It's a big pain. What an RTOS does is it takes a step back. With what we're going to be doing with Chibi OS is that things are broken down into drivers. You won't have to do as much register mucking about as you would with the AVR and the AVR-C. AVR-C is really just a step above machine code and assembly. Well, it's two steps. It's a step above assembly. So, you will still have to do a little bit of working with some of the simpler things, like telling the analog to digital converter what frequency to run at, how many bits to read, how many samples you want taken, that sort of thing. But you don't have to take care to go through the data sheet and figure things out. You don't have to take the care to go through the data sheet, figure out what every bit in every register does. You don't have to worry about the timing of everything. It's all done for you thanks to drivers and layers. So you have the hardware. Here's what I mean by layers. You've got the hardware layer, and on top of that sits the OS, or the kernel, and then you have your software. So the OS, the Chibi OS, the RTOS, takes care of interfacing with the hardware in it's all handled through libraries and such, but it allows you to not to have to deal with so much of the lower level things, like I said, with bit shifting, time, all that sort of stuff. It lets you just focus on writing the actual software. And things like drivers. You have drivers written for the analog to digital converter. You've got things written for SPI and RS-232 communication. Even USB communication has drivers written out for it so that you don't have to figure out what's going on. You don't have to send specific messages to get your code to work. It's all very well taken care of. This is all just cleverly written software. Using an RTOS, this is where we make the distinction between a software program and a hardware program. There we go. What's the difference? Software. Let's start with hardware. What we do with AVR-C and the AVR, that's hardware. You're writing code which directly interfaces with the architecture. You're dealing every line of code you write in some way directly controls a piece of the chip. You're communicating directly with the registers, you're communicating directly with the ALU and the instruction decoder. You're doing everything directly. There is no level of abstraction. There's no level of you talking to some other piece of software, or in this case, hardware. Or hardware. You're not talking to a piece of hardware program. That's what this is, the OS. Software is things you'd write in C++, things that you'd write on a very high level. It interacts with the operating system, which then interacts with the hardware. So things like Word and things you run on your computer normally, that's software programs. Those are things where the developers didn't have to worry about, oh, how much RAM allocation do I have to deal with? Oh, I've got to work with the display drivers. No, everything's taken care of by the OS. So this is where we're making the distinction. We're now delving more into the software side than the hardware side. So that's abstraction. It's removing yourself from all of the hardware you'd have to deal with and making things easier through drivers and layers. So you're going to be seeing a lot of layers when we start talking about the inner workings of the Chibi OS. Now, the second thing that makes an RTOS what is an RTOS is generally some sort of task system. Now, you can have a task system without having an RTOS. There are multitasking systems that you can get for almost any processor architecture, even something as simple as the AVR. I keep going back to that because it's my most favorite architecture. But what a task system does is, and I'm going to move this so that we can look at a pseudocode example, not a strict code example, but a pseudocode example. I've got this in Notepad++. Let's say you want to write some code. Let's say you're developing a robot. Nah, let's take that back a bit. Let's start with this. What you write, your code, has to deal with the real world, and it has to deal with inputs and outputs, and it has to be able to communicate at a pretty high rate. This is something I like to call awareness. How aware your device is to the rest of the world, how well connected it is. So let's say you're building a robot, and it has an ultrasonic distance sensor attached to the front, and you want to know how far away it is from something. And let's just make this a simple Boolean operator. It's greater than 25 centimeters away or less than 25 centimeters away. So what I've got here is a pseudocode example of that. So let's say you want to drive up to a wall, say up to a 25 centimeter distance, and then stop because you've gotten too close. There are two ways you can handle that. The first way is with this, with a while loop. And in that while loop, you're going to say while not that event, while you're at a distance away from the wall. You're going to wait. You're going to keep driving forward, but you're going to keep checking over and over and over again that you are not that distance away. But when you are that distance away, you cut out of this loop, and then you do something else. You stop, you whatever. This is called a blocking method. What happens is this is the only thing that's run. Nothing else happens. You've limited your device's amount of awareness to only this, to only that sensor. So nothing else can be run while it's checking for this. And that's called blocking. Obviously, that's not that great, but it's all you've got with single process. Now, with this, you can have a constant loop, and you're just going to check every now and again in that loop. So it's similar to this, but you're not blocking what's going on here. So you can say, if this event, then you're going to do something. You're going to stop, or whatever. But if it's not this event, it's free to do something else. It doesn't have to keep waiting. It doesn't block. You can be focusing on other things. You can be doing math. You can be checking other sensors. You've increased your, or you've brought back a level of awareness. You've brought back how well it is able to be aware of its outside world. What's the problem with this? Well, the thing about this loop is the placement of your check has a lot to do with how it's going to respond. Say what goes on in this section of the code takes a lot of time. You've now reduced the amount of time, or you've now increase the amount of time between when this checks. So it might not stop at 25. Your robot might not stop at 25 centimeters away from the wall. It might stop at 20 or 15 or 5 because it takes a certain amount of time for it to execute this bit of code and then come back to check. So while you've increased the amount of awareness, you've had to split that and you suffer for it. So what can you do? Well, the issue with these two systems is that it's single line processing. It only does one thing at a time in a specific procession. This is what a task system is supposed to do away with or reduce. A task system lets you have, say, task A and task B. And then you've got lines of code in task A and lines of code in task B. What happens is there is a timer. And this timer is set to go off, say, every 100 clock cycles or every 10 clock cycles. It can be really fast or it can be a little slower. And what's going to happen is the timer is going to go off, and then it's going to check. It's going to look at whatever task is running. It's going to say, OK, stop. Now remember, the stop is very short. When it stops, it's going to then check priority. Priority, yeah, there we spelled that right. Each task, when you create it, is assigned a priority level. So, say you need to check the distance sensor. That's assigned a very high priority. So you don't have to check it all that often. It's still checked, but it's checked and then it goes back to task A, exactly where you left off. You don't have to execute all of task A before you can check again. So you'll execute one line, check. Execute another line, check. Execute another line, check. Now, the other part of priority is if that robot has come within that distance and the timer flips over to task B, it says, OK, what happens here has a high priority. We need to stick with task B for a little while longer instead of jumping back to task A. Task B has a higher priority than task A. So it's going to stay in task B and finish before it jumps back to task A. So this is a little like hardware interrupts. The difference being hardware interrupts are limited by your device's hardware. So something complex like a distance sensor, you might not have a hardware means by which to check that to say 25 centimeters or 50 centimeters. Or if you do have that, you might not be able to adjust the distance. So what a task system does and a priority system does is it lets you assign anything a priority, any check you want to have a priority. And you can check that with the timer. This is something the RTOS does for you. And it's able to jump back and forth, constantly checking, and then grabbing a hold of it based upon its priority when it needs to grab the processor's attention. So it has a lot better flow than these two. So that is what an RTOS does. Those are the two big things that an RTOS will do. And those are two things that we're going to be discussing when we deal with the ChibIOS and the discovery board with a name that's a pain to say out loud. So that's what an RTOS is. I hope I explained that clearly. But again, if you have any questions, leave it in the comments. But I'm Human Hard Drive. Thanks for watching.